All right, we are coming back from break. We've been looking at a number of examples of length contraction and examples of time dilation. And we've got one more example here with the length contraction. So let's take a look at this. It says that we have this really fast train with a length of 500 meters. It's going through a 200-meter long tunnel. Is it possible that the train could be going so fast that the entire train, the train which is 500 meters at rest, could be length contracted to 200 meters, which would allow it to be entirely inside the tunnel at a particular instant? And you're going, yeah, of course. There's no reason that we can't get a train which at rest is 500 meters, that length contracts to 200 meters. It's just going to have to be going really fast. I'm not saying we can design one and build one. I'm saying, theoretically, sure, if we can get the train going fast enough, we can have it fit inside that tunnel. So here it is, at rest. The train is 500, looks like a really long hot dog or something, 500 meters long. The tunnel is 200 meters long. Clearly the train doesn't fit. But wait, let's have the train go really, really fast. We'll have it go so fast that it length contracts from 500 down to 200 meters, and then it's going to fit inside the tunnel, no problem. So let's see how fast that would be. Using a length contraction formula, that would be L naught over L, 500 over 200. I just need a gamma factor of 2.5. Now this is an important equation right here. Let me stop and say, what we've been doing up until this point mostly is they give us a value of V and we calculate gamma. But in this instant, we're going to do it in reverse. There's a value of gamma that we want, and we want to know how fast we have to go to get that value of gamma. This is the very same formula, it's just been flipped around. So it's been written so that I can put gamma in and use it to solve for V. So I would say keep that in your notes too. Keep both formulas in there, unless you want to, derive it on the fly during an exam. But what we can do then is say that V is equal to C times 1 minus 1 over gamma squared, square root. Putting all the numbers in, I ended up with a speed of 0.9165 C. So that's all we got to do, right, is build a train that can go 0.9165 times the speed of light. That's really, really, really fast. Okay, but if the train were really traveling that speed, then length contraction would take place. The train would be 200 meters long, and it's going to fit inside the tunnel. Now, how do we know that it actually fit inside the tunnel? Well, because we placed observers at the front of the tunnel, at the back of the tunnel, and observer A is going to record when event A occurred. Event A is the front of the train reaches the tunnel. The front of the train is just starting to exit the tunnel. Event B is being recorded by observer B, and they're going to get exact time at which the back of the train reaches the tunnel. And so the observers A and B are in the rest frame of the Earth. They're in the reference frame of the Earth. And so their timing devices are synchronized, and they're going to be passing at this, time's going to be passing at the same rate. And what they find is they measured the instant at which events A and B occur, and they verify, yep, simultaneous, front and back end of the train were both in the tunnel at that one instant. Now, there seems to be a problem with this, though, because the observers at rest on the surface of the Earth are able to demonstrate that the entire train, the length contracted train, it's only 200 meters now, fits inside the 200-meter tunnel. At one instant, it's entirely inside the tunnel. Let's flip this around and ask, what about observers on the train? What will observers on the train observe? What will they find as they go through the tunnel? Well, if we move into the reference frame of the train, then the train's at rest. And all the passengers inside the train, they can do the measurements themselves. The train is clearly 500 meters long. So the train maintains its 500 meters of length. And what's going to happen is the tunnel is going to be length contracted. The tunnel's length was 200 meters, but in the reference frame of the train, the tunnel is moving towards the train, and the tunnel is moving towards the train at that very same 0.9165 C, the very same gamma factor of 2.50, and so in the reference frame of the train, the tunnel is only 80 meters long. There is no way the train fits inside the tunnel as the tunnel passes over the train. So here comes that tunnel at the high speed. It's only 80 meters long, and so here it is when it gets to point A at the front of the train. Clearly the entire train is not fitting inside the tunnel. And then here we go, along the train, the tunnel passes over the train. Here we get to point B, and then the tunnel continues on at this high speed. So clearly event A happens before event B. They're not simultaneous. Is that a problem? And it turns out it's not. So in special relativity, two events that are simultaneous in one reference frame in general will not be simultaneous in other reference frames. So simultaneity is not something that generalizes to different reference frames, and it turns out that there's no problem, there's no deep philosophical problem, I guess I'm going to say, that prevents us from accepting the idea that these events are not going to be simultaneous in the reference frame of the train. So event A precedes event B, and we can even go in and determine by how much. So we can say that the train has a length, or the tunnel now has a length of 80 meters. From this position, where the tunnel has just reached the front of the train, back of the tunnel, to this position, how far has the tunnel moved? And the tunnel will have moved 420 meters, because the train's 500 meters long, and the tunnel itself is 80 meters in length. So from this picture to this picture, the tunnel has traveled 420 meters. Now the tunnel is moving at 0.9165 C, so it says that the time delay between the two events is 1.53 microseconds. Okay? I mean, that's not nothing, so that's an easily measurable quantity of time. So now the difficult part here is getting the train up to these incredibly high speeds. How fast did we have this thing? 0.9165 times C. Getting that gamma factor of 2.5, that's the difficult thing. But if we could do that, then we would find that there is this time difference between the two events. There's a delayed time in that reference frame. All right, another issue that comes up in relativity is adding together velocities. So if I have, well, really three objects. I have the Earth, and then I have a spacecraft which is moving at a certain speed with respect to Earth. And no, we have never launched any rockets that come anywhere close to the speeds we're talking about. So this is a really incredible speed, 0.60 times C. And then this is going to launch another rocket. So there's going to be a couple of, there's going to be the Earth and the rocket. So how should we deal with this? Well, here's the diagram I would suggest. Here is Earth's reference frame. Here is the first rocket's reference frame. I'm going to call that rocket B. And then here is the third frame. Here is rocket C. So here is Earth. Here is rocket number 1. Looks familiar. And then here is another rocket over here. There's a relative speed between the Earth and rocket B. There's a relative speed between rocket B and rocket C. I can write down those relative speeds. Now, those are the values that they've given us. They've said that there's a relative velocity. There's 3 of these relative velocities to keep track of. They've given us 2 of them. So VAB is 0.60 times c, and just by coincidence, VBC also is 0.60 c. What's the formula for adding velocities together in special relativity? And the formula in special relativity, it's this. The formula in special relativity says add the 2 velocities together as you would in classical physics, but you're not through. You can't just add them together. You have to divide that number by 1 plus VAB over C and VBC over C. When we do that, we get 0.60, 0.60. Now the 2 0.60s combined add up to be 1.2 c. That's faster than light. Relativity says there's no such thing as 2 reference frames that are moving faster than c relative to each other. Now we'll find out in the very last chapter of our textbook, when we look at astrophysics and we start looking at expansion of the universe, we'll find out that special relativity isn't the final word on this, that general relativity allows for space to expand, and if you have expanding space-time, then you can find reference systems that are moving relative to each other at speeds faster than c, and we'll talk a little bit about that more when we get to that final chapter in the course. But for now, special relativity is saying that the relative speeds are going to have to be less than c, and that happens mathematically as a result of these extra terms that special relativity shows us are present in the derivation, and that says that reference frame A and reference frame C, the relative velocity between them is only 0.882. So just following the formulas. All right, we're quite a ways into this chapter, and we've spent a fair amount of time talking about distances and time intervals, and those are fine, and you want to be able to work those problems, but the most important problems that we're going to do, the most important things we're going to learn in this chapter have to do with formulas for energy, kinetic energy, momentum, and how they're all related to mass. So this is actually the most important part of the course. The most important part of the chapter, not the entire course, just this chapter. So here are the 2 energy formulas that come from special relativity. The first formula here, I'm going to drop to this lower one first, says that the total energy of an object includes something called its rest energy. Now the rest energy of an object, E equals mc squared. Now I'm told that E equals mc squared is the most recognized formula in all of science. That more people say, oh yeah, I've heard of that formula, E equals mc squared. Also, E equals mc squared is probably the most misunderstood formula in all of science. What does it mean? And the typical response is, it means that energy equals mass times the speed of light squared, done. But that really hasn't told us anything. So we're going to have to take a look at a number of examples here. What E equals mc squared tells us is this. So special relativity does introduce this formula, and it says that up until now, we've had this principle called energy conservation. And energy conservation says that if we carefully keep track of all the energy of everything that goes on in some kind of a reaction, that we can account for all the energy and where it goes. That there's never an instance of where energy just appears from nowhere, or where energy just disappears, but that we can always follow the energy. There's a fixed amount of energy in a given system, and we can use that to actually solve problems. The new piece of this is that relativity tells us that there's a new type of energy. It's almost kind of like a potential energy, in that if I have an object with mass m, I can assign, in terms of bookkeeping, I can assign a certain amount of energy to that. Now, where is that ever going to show up? Because we have successfully, very successfully I might say, gotten through 35 chapters of our textbook. We have gotten through a semester and a half of physics, and we've never had to go back and use E equals mc squared, not once. So why is it that this hasn't shown up yet? This only becomes an effect if we run reactions where the objects going into the reaction and the objects coming out of the reaction have differences in mass. What this formula is saying is that we can take a certain amount of mass and actually convert it into kinetic energy. So what it says is, in a reaction, what we can do is take the mass of all of the reactants, everything that's going into a reaction, take all the masses and all the kinetic energies, and then run the reaction and then look at everything that comes out, and then look at all the masses and all the kinetic energies. And it says that the masses themselves are not necessarily conserved. Now, I know in chemical reactions, for example, we work from the assumption that mass is conserved. That's not strictly true. It just turns out that in chemical reactions, the small differences, the mass of the reactants and the mass of the products, they're so similar that in practical terms we can assume that the masses have been conserved. But once we get to nuclear reactions, which we'll see in the course, it becomes clear that the masses are not conserved. That the masses we start with and the masses we end up with are measurably different. What has happened to the mass? Well, if there's mass that has gone missing, that shows up as kinetic energy, and vice versa. We can have reactions where there's a lot of kinetic energy going in, but not so much kinetic energy coming out. What's happened to the energy? It's been converted into mass. So in some sense, E equals mc squared is telling us that in a reaction we could take a certain amount of mass, and that can be converted into kinetic energy. This is in some sense available to be converted, but it only occurs for particular types of reactions. There are only particular types of reactions where the mass before and the mass after are measurably different, where this formula is going to come into play. Okay, so that's the story with E equals mc squared. Now, this formula is relating kinetic energy. Let's go back and look at this one. This one's a little more complicated. This is actually the more general formula from special relativity. And it says that this total energy, the energy that includes the mass of the object and its kinetic energy, if I take that total energy squared, it's equal to mc squared plus pc squared. Now, these two formulas that relate energy and momentum and kinetic energy and mass, they make a couple of predictions. And that is, first of all, there's two categories of objects, or two categories of particles in nature. We could have objects or particles that have no mass at all, and our best example of that is the photon. So the photon, we've done really careful measurements. We've really, really limited what the possible mass of a photon could be, and we're really kind of invested in the idea that the photons have no mass. Okay. Now, for massless particles, that's not a problem. I just put a 0 here and a 0 here. And what these formulas turn into for a massless particle like the photon is that the momentum of a photon and the energy of a photon are related by that formula. I can take the momentum of a photon, multiply by c, which is basically just changing the units, and that tells me how much energy the photon has, and vice versa. I could start with either one of these. Also, the second formula tells us that for photons, all of the energy is kinetic. So photons definitely have energy. They don't have mass. Their energy is kinetic energy, and they also have momentum. Now, if we have objects that do have mass, it turns out that the total energy can be written, now we haven't shown the derivations on these, but the total energy can be written as gamma times mc squared. And the kinetic energy then can be written as gamma minus 1 times mc squared. And the momentum, there's a couple different useful formulas here. Momentum times c is equal to gamma squared minus 1 square root times mc squared. And then we could also write that as gamma is equal to, momentum is equal to gamma times m times v. So this doesn't look much like kinetic energy 1/2 mv squared, but we'll show that the two formulas are related. And then this looks pretty similar actually to our momentum formula of mv, it just has a factor of gamma. And as far as the kinetic energy, if you remember, we said when an object is going really, really slow compared with the speed of light, that the gamma factor can be approximated as 1 plus 1/2 v squared over c squared. If we plug that into the formula for kinetic energy, we find that at low speeds, the kinetic energy formula is given by 1/2 v squared over c squared times mc squared, which gives us 1/2 mv squared. So the way this works is special relativity is more general than classical physics. We can start with special relativity and put in these low speed approximations. The formulas we get back are the formulas that we learned back in physics 3a. So the classical physics formulas can be derived from special relativity, but of course you can't do it the other way around. The classical physics formulas are the ones that are limited. The special relativity formulas are the ones that are more general and include not just low speed, but high speed effects. Okay. Here is a moving electron. I'm just going to jump ahead right to the slide here. So here's an electron, proton, neutron. This seems like a good time to just kind of go through some basic properties of electrons, protons, and neutrons, because we're going to run into them. We're going to run into these guys a lot over the next rest of many weeks of this semester. In terms of kilograms, here are the masses. And what we notice is that the neutrons and protons have almost the same mass. Look how similar those are. But that the electron is much, much lighter. The protons and neutrons are 1,800 times more mass than the electron. And then what we're going to find later in the course is that the electrons are fundamental particles, and they're a fundamentally different type of particle than the protons and neutrons. The protons and neutrons are in some sense the very same particle, but the neutron is the neutral version and the proton is the charged version. But the electron is a fundamentally different sort of particle. Okay, so these masses match up. Now, often, instead of using the mass in kilograms, more often than not, we're going to be using the formula mc squared. So the mc squared value for an electron, its rest energy, its mass energy, is 511,000 eV. So that's 511,000 eV or 511 keV. And once we get down to the level of particles, we're going to be using these eV energy units a lot. We first introduced these back in chapter 23. I know that was a long time ago. But now we're going to come back and use the eV units a lot. We're going to use them relentlessly. So the proton MC squared value is 938.3 million, or mega, eV. And the neutron's mass is 939.6 MeV, or again, mega eV. If we write those out, that's what it would look like for comparison. All right, so let's take a look. It says that what we're going to do is we're going to look at an electron. It's inside what they say is a cathode ray tube, but basically it's an electron beam that we've generated, and the electrons within this beam are going pretty fast. They're going 4 times 10 to the 7 meters per second. Well, let's find out what the gamma factor is. Plug it into our gamma formula. Turns out those electrons have a gamma factor of 1.00901. So it's not a huge effect at this speed, but it's measurable. The energy of these electrons, the total energy, is given by gamma mc squared, so let's calculate that. Now the mc squared value for the electron was 511,000 eV. For an electron going this fast, the total energy is going to get a boost by the factor of gamma, and that brings it to 515,600. Well, how much of that is mass energy and how much is kinetic? And I can calculate the kinetic energy by taking gamma minus 1, and that says 4,600 eV. All right, so this is the mass energy of our electron, 511,000, and what we've calculated is at this speed, the electron, in addition to its mc squared energy, now has kinetic energy as well, and so we got to add this on to get the total energy of that electron. In a reaction, it's the total energies that are conserved. Now, how much momentum does it have? And here we have an option. We could use either of those formulas we presented. Typically, when we're looking at particles, we are going to measure the momentum in terms of eV. Now, why are we measuring momentum in eV? And you just have to practice doing these calculations, and after a while I guess you get kind of used to this. But the idea is to measure E and K, kinetic energy, and momentum, and mass, all in the same units. So we put everything into the same units, and then we don't ever have to go through any units conversions. We can use these formulas. Everything's already in the same units, so units conversions is not an issue. So what we're going to do for momentum is we're going to calculate that as PC. Now the PC here can be obtained by gamma squared minus 1 square root times mc squared for our electron. So again, they're new formulas, but we're just plugging into them. So we just need to put in the mc squared value. This column of numbers becomes important. The gamma formula becomes important. The momentum of these electrons will be 68,750 eV. Now, what would happen if we went to a higher speed? I feel like that 4 times 10 to the 7, it seemed really, really fast, but it turned out it only gave us a gamma factor of 1.009. Let's go much faster, so let's try 0.98. At 0.98, we're going to get a gamma factor of 5.025. At this speed, we're going to have more kinetic energy, and we're going to have a total energy that looks like this. Now, let's take a look and see, at relatively low speeds, it was still the mass energy that dominated. The electron's mc squared value is 511,000, and in part A, the additional kinetic energy wasn't that big compared with the electron's mc squared. But in part B, we're going much faster. The gamma factors have gotten much bigger, and now the kinetic energy is the dominant effect. And that's what happens. So with these particles, they start off with a certain amount of mc squared, a certain amount of rest energy, and then at first maybe there's a little bit of kinetic energy, but as we go to higher and higher speeds, the kinetic energy begins to dominate. Okay, and then the momentum is 2517. Now those numbers were in EV. These numbers are in thousands of EV, but you know, kind of stare at those and practice playing around with the formulas. That was a good example. Now, we had these spacecraft problems earlier, and we were talking about how much time it would get to a distant planet, and if we go fast enough, the astronauts actually wouldn't necessarily experiencing, they could get out to a distant planet in just a few weeks and come back in just a few weeks. If they travel near light speed, they can be out there very rapid and come back. Now when they get back to Earth, it could be, you know, tens of years or hundreds of years have passed. But the astronauts themselves, if they're going fast enough, could get out there in pretty short times. Is it practical to take a spacecraft, let's say the space shuttle, that has actually been retired now for quite a few years. I hope you guys remember the space shuttle. Space shuttle has a mass of about 100,000 kilograms. So let's do this. Let's take the total annual energy production of the entire planet. All the power plants, all of the energy that we use on this planet in an entire year works out to be about 8 times 10 to the 21 joules. Let's take the entire energy output of the entire planet for a year, and let's use that to speed up the space shuttle, a 100,000 kilogram spacecraft, and see how fast we can get it going. See if we can launch it out to some distant star. Now, the kinetic energy then would be 8 times 10 to the 21 joules. The mass energy of this space shuttle, if I take m, and now this time I'm actually going to put in 3 times 10 to the 8th meters per second. I said we don't do that very often, but in this case we are going to plug in mass in kilograms, c in meters per second, and it says that the mc squared for a spacecraft the size of the space shuttle has enough energy equivalent to that of the total energy output of the whole planet for the year. So that says that the gamma factor that we can get to with this spacecraft by using all of this energy is 1 plus k over mc squared. That's coming from our kinetic energy formula that we wrote down. We can only get up to about a gamma factor of 2. Even with a very modest size spacecraft, something the size of the space shuttle, we would have to take the annual energy output of the entire planet just to bring it up to 85% of the speed of light. Okay? So a gamma factor of 2, that's not very impressive. We're not really going to be able to get out to that distant planet that much. We're not going to save that much time in terms of the time that passes for the spacecraft. So we have serious energy limitations until we find an energy source that is much more powerful, able to produce much more energy very rapidly. We don't know how we would reach those really high speeds that we were talking about. Okay, let's set the spacecraft aside. Let's get back to some fundamental unstable particles. We talked earlier about these things called muons. They were discovered back in like the 1930s, coming in through our atmosphere from reactions from high energy particles, from the sun and from other things going on in outer space. So a pi neutral meson, that's what these pions are, they're particles, they have a certain mass. Now they've given this in kilograms. They say that they're traveling at 0.80 c. They've given us the speed in meters per second. They're saying, what's its kinetic energy? So let's do that. Let's find out the kinetic energy of a particle. So here is this particle. It's traveling at some speed. Now they gave that to us in masses in kilograms. V is in meters per second. But what I want to do is I want to convert that over. What I'm going to do is I'm going to take the m, multiply by a couple factors of c, and that gives me 2.16 times 10 to the minus 11 joule. So everything we've been looking at in terms of doing energy and momentum and kinetic energy calculations, we're typically working in terms of mc squared. And then I'm going to take those joules and convert them into EV. So I got to use the 1.6 times 10 to the minus 19 joules equals an MV. So I got to do the conversion factor and convert into EV. Now the speed here is 0.80 c. So the classical calculation of kinetic energy would be 1/2 mv squared. Now that's a classical formula. You would think I would plug these in, but instead I'm going to do a bit of a roundabout. I'm going to write the classical kinetic energy as 1/2 mc squared times v over c squared, and then I'm going to claim it's a shortcut. And here's why. So what I can do then is I can put in the 1/2. For the mc squared, I can put in this 135 MeV that I've calculated. For v over c, I can put in 0.80. So the idea is to work in terms of, again, mc squared and v over c. Now what that says is the classical prediction of 1/2 mv squared works out to be 43.2 MeV of kinetic energy at that speed. Well, that's not going to be right because it's classical physics. And so what we're going to have to do is use the relativity formula. We know that at 80% of the speed of light, the gamma factor is going to become important. Let's see what relativity says the actual number is. So the actual kinetic energy at that speed would be gamma minus 1 times mc squared. The gamma value calculated from here is 1.67. Using the formula for kinetic energy, 1.67 minus 1.00 times mc squared, says actually the kinetic energy is 90. So let's kind of flip around this description. We could say how much energy would a pion require, this fundamental particle, how much kinetic energy would it require to bring it up to this speed? Classical physics says 43 MeV of energy, but relativity says no, it's not. It's 90. It would require more than twice as much energy to bring it up to that speed. And that's what we find with all these examples. As you get closer and closer to the speed of light, you end up using more and more energy to asymptotically approach the speed of light. So relativity says there's no limit to how much energy you could transfer into this particle, but it says no matter how much energy you do transfer, it's never going to reach c. It can asymptotically approach the speed of light, but because this particle has mass, it won't ever quite get to the speed of light. It would take more and more energy to get it closer and closer, but it's never going to quite get there. So here's an example. Let's take a look at this. We've got, this was the pion kinetic energy. Here we have energy from a nuclear reactor. And so this is the mass of a uranium, or it's, I'm sorry. This is just radioactive decay. So this is a uranium nucleus decaying through alpha decay. We'll see this in a few chapters, into thorium and helium. What's the energy release look like? And what we were claiming a while ago is that we can take a certain amount of mass and convert it to kinetic energy. Let's see how this works. So this is a nuclear reaction. It's taking the nucleus of uranium-232 and converting that into, well, a helium nucleus separates out. A helium nucleus is 2 protons and 2 neutrons. So we're going from the mass of the uranium, which is very close to 232, into the mass of helium, which is very close to 4, and the thorium, which is very close to 228. But when I take the uranium mass and subtract off the mass of the thorium and the helium, there's mass missing. The mass of the products is measurably lower than the mass of what we started with. How is that possible? And the simple answer is mass is not conserved. It's total energy that's conserved, which says that if mass goes missing, it must have ended up as kinetic energy somewhere. So we can take some amount of mass and convert it into kinetic energy. So here we're taking a bunch of mc squareds, and that's getting converted into this much kinetic energy. Now we're going to do a bunch of this stuff when we get to chapters 41 and 42, looking at nuclear physics. And for now, let me just leave it at these masses were given in atomic mass units. There's a conversion from atomic mass units into MeV. So there is now, because of E equals mc squared, there are conversion factors that say a certain amount of mass corresponds to a certain amount of energy according to that formula. And it turns out that for every atomic mass unit of mass, that's the equivalent of 931.5 MeV. And that says that the kinetic energy that was released in this reaction is 5.41 MeV. So up until now, when we have these large amounts of kinetic energy released in a reaction, I guess we haven't necessarily said where is that energy coming from, but now that's the question we're asking. Where did this kinetic energy come from? It didn't used to be here. Oh, it came from mass. So the stuff that this decayed into doesn't have as much mass, and that mass difference can now be calculated in terms of how much kinetic energy was released. So let's see. A couple of quick conversions here. So 1 gram is the equivalent of 9 times 10 to the 13 joules. That's a lot of energy from 1 gram. 1 atomic mass unit is 931.5 MeV. And then there's just an outline of the reaction. So the takeaway here is mass is not conserved, and when mass is missing, we can use that amount of missing mass to calculate how much kinetic energy was generated in a reaction. Okay, here's a proton that's being brought up to enormous energies. So this is in a particle accelerator. This is actually in what's called the Large Hadron Collider on the border of France and Switzerland. The kinetic energy for this proton is 6.5 TeV. Now T is a million times a million. It's a trillion. So that would be 6.5 million MeV. The mc squared for a proton is 938.3 MeV. So we can find out the gamma factor. How fast is a proton going inside the Large Hadron Collider? Now, with this much kinetic energy, you can see the kinetic energy is much. This is a 6.5 million MeV compared with about 900 MeV. The gamma factor for this, plugging numbers into this formula, becomes 6,927. And when we solve for V, don't try this in your own maybe try this in your calculator. Maybe it will work. Yeah, I think it does. So I was thinking it wouldn't keep track of it. But it did work out to be 0.9999990 something 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 times C. So that gives you an idea of, in the world's most powerful accelerator, collider, protons are being brought up to speeds of 0.9999990 C. All right, so that uses protons and antiprotons. Now, just to give you a comparison, when I was in graduate school doing graduate research, I worked at our collaboration was running experiments at the Stanford Linear Accelerator just down here on the peninsula. And we were using not protons and antiprotons. We had a storage ring, and it had electrons and anti-electrons in it. Now, as we've talked about, the protons are 1,800 times as much mass. And so our kinetic energies were a very modest 14.5 GeV. GeV, that means a billion EV, that's giga versus mega. So this would be 14,500 MeV. Now the masses of the electrons are much less. When I plug this very modest amount of kinetic energy, this is so much more kinetic energy here, into this formula, it turns out that the gamma factor of our electrons, when we were running experiments back in 1993, was 28,000. And so our electrons were traveling at 0.99999999379 times c. Our electrons from that experiment in 1993 were faster than the current highest energy protons are at the highest energy collider in the world. Okay, and that's because we were using these low mass particles. So putting not as much energy in, but using low mass particles, these were brought up to much higher, well, much closer to C. Let's say that. It's not really very different. It's just that this is much closer to C than that is. If I take the difference between that number and C, this has reached most of the way there. And again, I apologize for putting these all in different units. Let's do something to get a better comparison here. This 14.5 GeV would be 14,500. That would be 14,500 compared with 6.5 million. All right. Okay, all of the formulas here, all of the formulas that we're working with here, if we have low speeds, go back into classical physics. So again, classical physics is included in these formulas that we're using. So I'm going to do a little bit of background for special relativity and talk about what kind of some of the fundamental ideas are. This stuff I don't think you guys have to worry about. So this is mostly just for your information. But the formulas within special relativity actually take time and space and mix them together. They say that what is a time interval in one reference frame gets converted into a distance in the other frame. So in one frame, we take a certain amount of length and a certain amount of time interval and convert that back over into a distance. And the same thing happens with time. The time measurements in one frame get combined with distance measurements to give the time measurements in another frame. So these differences, these length contractions and time dilations, are actually related to how space and time get added together in special relativity. I don't know how you guys feel. I do not experience space and time the same way. My experience of distance is not the same as the experience of time passing, but mathematically there is this very tight connection between amounts of time and amounts of distance. These are some of the formulas that get used in order to measure time interval and distances in one frame compared with another frame. The conversion that we use, I don't know if you guys have done matrix multiplication, but it's called a Lorentz transformation. It can be represented in terms of matrices, or it can just be written out algebraically. And the point this is one of the aesthetic parts of the course. The formulas are beautiful. It says that we take equal amounts of space and time, the same way that we convert from space and time into time. When we switch the formulas and reverse the x's and the t's, that becomes the very same formula for x. So the formulas are symmetric under exchange of space and time. Who would have thought? The other item that comes up for us, and again, you don't have to worry about any of this, but we work in terms of four-dimensional vectors. So now that we've combined space and time into a four-dimensional space-time, what happens is we use four-dimensional vectors that include a time component as well as an x, y, and z component. And that's why C is a conversion factor. If we're going to move into a four-dimensional space-time, then we need to know how many meters and are equal to how many seconds, and that's what C is. Now, another four-dimensional vector is the total energy momentum vector. And you guys are saying, oh yeah, I always suspected that momentum and energy were kind of the same thing, and they are. Energy is the time component of momentum. Momentum components are the space components. So we can actually go back to the super fast train. I'm not going to go through the details here either. But what we can do is we can take the formulas that we wrote down for starting with time intervals and distances in one frame, and use these formulas, the Lorentz transformation, to just calculate the passage of distance and time in the other frame. So the numbers are all outlined here, but again, you guys are certainly not responsible for any of these items. It's just a way to go in and show what's kind of going on in the background. Now, one last example, one last formula that we want to go through and derive, and you guys, the derivation is, you guys just want to be able to work from the results. You don't have to go through the derivation and derive it. So if I've got light traveling by, let's say we've got some light traveling by, some photons coming by, and I measure how much energy that photon has, and then I ask myself, in another reference frame, how much energy would that photon have? Now, if the photons are coming towards me in this direction, I'm looking over, the photons are coming towards me, what that tells me is, if I move into a frame headed towards the photons and look over to see how much energy they'll have, they will get measured as having more energy. So it works the same way in relativity as classical physics. If an object is coming towards me with a certain amount of kinetic energy, how would I have it end up with even more kinetic energy? Well, I could move into a frame moving towards that object, and in that other frame it now has more kinetic energy. So with photons, because photons have the momentum of a photon matches the energy, we can write these four-dimensional momentum vectors. We can carry out a calculation, and what we can show is that the energy of the photon, let me see if we have a follow-up result here. Yeah, so this is referred to as the Doppler shift for light. Now, we did a Doppler shift for sound. The Doppler shift for light is not the same formula. Sound is a mechanical disturbance propagating through some kind of a medium. It's actually the motion of the particles that make up the medium. Light's made out of photons. When light's traveling, it's the photons themselves that are actually making the journey through space. So fundamentally, sound and light, they're just really very different phenomena. Now the Doppler effect for light says that the energy of the photons measured in frame S will equal the energy of the photons measured in frame, in S prime, measured in S times C plus V over C minus V to the 1/2, where C is the speed of light and V is the relative speed between the references. Now, quantum mechanics tells us that the wavelength of a particle, a photon, an electron, a proton, whatever, the wavelength of whatever particle I'm looking at is given by Planck's constant, which we'll see in a few weeks, so we're not there yet. You may have seen this in some other classes. But the wavelength depends on the energy. And so I can take the energy formulas that we just derived and turn those into wavelength formulas. And it says that, let's say we have some red light coming towards us. Now the red photons aren't as energetic as blue photons, but if I go to a different frame and now measure the photons going by, first of all, they're going the same speed. So moving into a different frame doesn't make the photons go any faster. but it does have an effect on their energy. They now have more energy than they did in the other reference frame. So if I move into a reference frame going at some speed v, the wavelength shortens, the energy goes up. We call that a blue shift, and that represents now photons. The photons now have more energy in this new reference frame than they did in the reference frame I used to be in. Similarly, we can move into a reference frame moving away from the direction where the light is coming from, and as we move away from that direction faster and faster, when we look over and measure the energy of the photons now, they have less and less energy. So that's the Doppler effect, and it has to do with the energy of the photons, and we can turn that into wavelength formulas. So we could go with, well, the wavelength formulas that we have here and here. The red shift and the blue shift. Blue shift is if we move towards the light, the photons in our reference frame now, in our new reference frame, now have more energy, and if we're moving away from them, the photons will have less. Okay, so this last example, I hope, we've got one more item here. Thank you for your patience. I do want to get to these last couple of examples, so I'm going to go ahead and run through these at a sensible rate. It says here that a driver went through a red light because a driver ran a red light. So drivers in a hurry go through a red light, and sure enough, there was a police officer nearby, stops the person, and tells them, they said, you realize you just went through a red light. And the person thought, should I say I was just in a hurry? That's not a good idea. I will tell them it was a Doppler effect. And so the person who was driving says, had taken physics and understood the Doppler effect and said, you know, was that a red light? Oh, in my reference frame, it was a green light. Because in my reference frame, the photons had more energy, they had a shorter wavelength, and so I viewed that as green light. I apologize. I was just following what I was observing in my own reference frame. The police officer also had taken physics and sat down and did a couple of quick calculations. So red light is at a wavelength of 700 nanometers. Green light is at a wavelength of 550. So how fast would the driver have been traveling to have the light from a red light be green light in the driver's reference frame? So we can start with the Doppler wavelength formula. The wavelength observed by the driver equals the wavelength of the light in the rest frame times c minus v over c plus v square root. We can square both sides of this equation, and we can then solve for the velocity. We can factor out v. V then would be equal to c times the original wavelength squared minus the Doppler shifted wavelength over the original wavelength squared plus the Doppler shifted wavelength. Putting all those numbers in, the police officer got out the calculator and said, you were traveling 0.382 times the speed of light. Let's see, it's $10 for every mile per hour past the speed limit. Let's figure out what the cost of your ticket is going to be. So yeah, definitely the Doppler effect is going to happen, but a significant Doppler effect isn't going to happen at speeds of the driver going through the red light. Okay, last item that I want to look at. Again, this is one of those where you don't have to know the derivation, but we are going to be using the results. When we have particles that decay, and that's going to come up. It's going to come up in future chapters. We're going to be looking at, well, nuclear decay as one example, alpha decay examples. So we're going to be looking at examples where a particle decays into two other particles. Now, special relativity says what's conserved in these examples would be the energy, the total energy, and the momentum. So the energy of the original particle that was just sitting there at rest is its mass times c squared. So the energy of the original particle at rest is converted into the total energy of the other two particles. Now, momentum conservation says that whatever momentum particle 1 acquires, it has to match the momentum of particle 2. So we've got two equations, two requirements that nature has placed in front of us. Nature says, look, this is what has to happen in these reactions. Total energy has to be conserved. Momentum has to be conserved. What we can do is we can take those equations, take them through the formulas for special relativity. These are the formulas we end up with. It says that the energy then will be divided up according to this formula that we've written here. So these are the total energies. And then what we can do is we can do another page of calculations here and solve for the kinetic energies. So it says that if I define Q to be the combined kinetic energies of the two particles after the decay has happened, then these are the formulas that tell us how the kinetic energy will be divided up. So what's going to happen is, in all these reactions, M1 and M2 are going to be less than M0. There is going to be missing mass. The mass of the products is less than the mass we started with, and whatever mass is missing will show up as kinetic energy. Okay, and these are the kinetic energy formulas. So I think there might be a homework problem, maybe one, maybe two, where you can use these formulas now, but we'll see these in future examples. So take a look and see. In fact, I knew it. Here is the example coming up right now. So again, these are just particles that you guys probably have never heard of. We said that there was a heavy version of the electron called the muon. There's an even heavier version of the electron called the tau. And the tau has a mass of 1,777 MeV. This is one of the possible decay reactions for the tau. So all we're really interested in for purposes of this example is I need to know the starting mass and the masses of the two particles coming out. Well, one of the particles coming out is called the K1, and the other particle coming out is a neutrino, and the neutrinos, to a good approximation, have no mass. And so one of these is just going to be flat out 0. Well, that's not a problem for special relativity, so going back to our energy formulas, plugging the numbers in very carefully, I'm just plugging in the numbers that were given, dividing through by 2 times m0. It says that the K1 will end up with 1,342 MeV, and the neutrino will end up with 435 MeV. Now these two numbers combined have to be equal to the original energy, which was the mass energy of the particle that we started with, starting out with the tau. Now, this much mass went missing. If I take the mass of the tau and subtract off the mass of the K1 and the mass of the neutrino, there's 507 MeV of mass missing. Let's go and see where that went. And for that, what we can say is, well, the 507 MeV, it must have been converted into kinetic energies. The kinetic energy formulas that we came up with look like this. They actually make use of this Q value that we have calculated. Again, just plugging the numbers into the formulas that we've derived tells us that of the available kinetic energy, the K1, the heavier particle, gets the smaller fraction, and the lighter particle gets more. Now, why is that? Why is it that the low mass particle gets more and the high mass particle gets less? Because momentum has to be conserved. This is the way that the energy divides up in order to have momentum equal for the two particles. So it says that the kinetic energy of the K, that's 72.3 MeV, and the neutrino gets 434.7. Now the neutrino is basically traveling at the speed of light. Once we've assumed that the neutrino is massless, then we also have to make the assumption that it's traveling at the speed of light, or the speed of massless particles, let's call it that. Whereas with the K, we can use the formulas to determine its gamma factor, 1.05. The K1 actually is coming out of the reaction at 0.324 times C. So that's an example of a particle decay taking place, one particle decaying into two particles. If we know the masses of the starting particle, mass of the two particles that it decays into, we just run through the formulas. And that tells us how the energy divides up. Okay, absolutely last items in the chapter. Again, not anything you guys have to worry about, but maybe, just possibly, you're thinking, well, wait a minute. If you can't go faster than the speed of light, what would happen if you kept pushing on an object? If you push on an object, you're going to get an acceleration. If you keep pushing on the object's going to go faster and faster and faster. Eventually, you're going to be going faster than the speed of light. So, what happens in special relativity? This can't possibly be the correct formula. This allows the possibility of going faster than light. And you'd be right. The formulas in special relativity say that if you push an object in the direction that it's already traveling, the acceleration in that direction depends on the force divided by the mass divided by gamma to the third power. So you go, oh, of course, it's a bunch of factors of gamma, because when we're going really, really slow, gamma is basically 1. And that's why the special relativity formula simplifies into the classical formula at low speed. Now, what's also interesting in relativity, I think, is that if you're exerting a force in a perpendicular direction, say circular motion, then the acceleration in that direction is the force component divided by m divided by one factor of gamma. So the acceleration has less of an effect if you're accelerated in a direction that it's already moving compared with accelerating it from rest in a different direction. So if you pick a direction perpendicular to the current direction of motion, you get more of an effect from that. It's kind of interesting too. So special relativity then says the direction of force acting on an object and the direction of acceleration are not necessarily in the same direction quite. In classical physics, we made a big deal about that, right? All through physics 3A, we said, hey, if the force is in this direction, if the net force is here, the acceleration is in the very same direction. In special relativity, that's not quite true. Okay, now a second item that we want to do a comparison with is, what about electric and magnetic forces? Back when we were looking at electric and magnetic forces, we said that there is an electric force, which is Q times E, and there's a magnetic force, which is a cross product. And so that would be Q, Vy times Bz minus Vz times By. That would give us the force in the x direction as an example, and then we can go through and look in the other directions. In special relativity, the electric field components and the magnetic field components combine to form what we call a 4 by 4 dimensional tensor. This follows the rules for matrix multiplication. No, you are not responsible for this. But just to let you guys know, when you move on to special relativity, it turns out that electric and magnetic fields are the same thing. They're just different components of one tensor that we use in carrying out calculations. Okay, did we do this? I think we did. Thank you for your patience. We went on and on a bit there. Again, the Doppler effect, you want to be able to use those formulas. Those last two examples, those are just informational for you. All right, whoa, I went quite a bit over. Again, thank you for your patience. Whatever questions you guys have,
stop by, we'll get those questions looked at.